Hey everybody, good morning. So just announcements. I detected a couple of small typos in the notes. So I'm just going to show you. I've updated, I think, the PDF copy. Yeah, so it was on page 47 of your notes. This was in the proof of theorem 4.3, which was the linearity and product form for the continuity of, for the preservation of continuity. These were arguments showing that if functions were continuous, then any linear combination of them is continuous, and if functions are continuous, any product of them is continuous. These two yellow highlighted corrections are previously there was equals there, but that was incorrect. So so looking at this first example, what's going on in the movement from left to right here in that first relation of the first line? What's going on there is expanding, starting at the left, if you expand the brackets for the alpha f plus b to g evaluated at x and evaluated at a, you expand the brackets, so it's alpha f of x plus b to g of x. Similarly, for evaluated at a. And then you gather the f's together, factorize out the alpha, gather the g's together, factorize out the beta, and then you apply the triangle inequality. So it's the principle of triangle inequality for the absolute value being applied there that gives you that less than or equal. It's the yellow highlighted yet less than or equal. Previously it was an equal sign. Similarly down here in the product form, similar move going on, and we saw in our proof of the product rule for differentiation yesterday, we saw a similar rewriting of the difference of the products. Okay, but again, previously I had an equal sign here, but that's not correct. It should be a less than an equal sign, because this is involving, again, another application of the triangle inequality property for the absolute value. So when we're splitting the absolute value of the overall combination up into the sum of the individual absolute values, it's less than or equal to that sum. Okay? If you can make those corrections to your notes on page 47, and the online version on Google. Okay. Alrighty. So, where are we? So yesterday we were working through properties of the derivative. Okay? So yesterday we had properties of the derivative. We had the linearity property. Linearity we've done. Product rule we've done. And then we started to discuss the quotient rule and the chain rule. Today we're going to look at they're presented in the opposite order, so the quotient rule is presented first in the notes. We're actually going to prove it by discussing the justification of the chain rule. And then I'll show you how the other rules, the linearity, the product rule, the chain rule, can be combined together to give a proof of the quotient rule. So yesterday we did linearity of products. There's a short example here, an example 4.3 in the notes demonstrating the application of the product rule. But now we come on to proving the chain rule. For proving the chain rule, we're going to use a different approach. So the chain rule basically says that if we have a composition of functions which we want to differentiate, well, we might try applying the limit definition of the derivative, and that would be f after g applied to x minus f after g applied to a and that's all over the difference x minus a. So we could set off trying to prove it. Expand the brackets. But we get it to that kind of point. Now, previously in proving the linearity rule for differentiation and the product rule, when we got to this stage, we then started disentangling the f's and the g's and isolating in the numerator, getting the expression f of x minus f of a and g of x minus g of a, because they would ultimately, when we separated the fractions, they would turn into, take their limits, they would turn into the derivatives of f, the derivatives of g. It's a fairly straightforward separation in the case of proving linearity. In the case of proving the product rule, we had this kind of strange way we have to rewrite it. I'll just show you here. I've seen it a number of times. Yeah, so moving from that first line there, that's writing out the definition for the derivative of the product here in this line, and then you manipulate the numerator like this, and then do the separation and apply the definition. But it's not so clear how to do this. It's not so clear how to do this in the case of compositions, because the functions f and g are bound up together. Function g of x is supplying the argument to f, and g of a is supplying the argument to f over here. Okay? So it's not so clear. Not so clear how to deal with f and g separately here, like we did previously when we were looking at proof of linearity and the proof of the chain. So we maybe need a different approach. And it's great in mathematics when you can apply, when you get these techniques and tricks or ways, principles, ways of thinking. It's great when you get them and they work and you can apply them again and again and they work in different contexts. But it's also interesting and challenging when they stop working and when it's not so clear. So like proving linearity, proving product rule, we launched into the definition, messed around with the numerator, separated it out, and we proved the problem. Here we kind of run up against a little bit of a brick wall. It's maybe not so clear how to continue in the same thing. So we need a different approach. And what we're going to do is a different view, not completely different, but the same definition, but a different view of the definition of the derivative. Okay, that's what we're going to look at now. I won't give you a stream of notes, handwritten notes, because it's fairly well described here in the notes. This year I made a special effort just to get it all typed up nicely in notes, because it is quite important. So I'm just going to talk you through this page here just to show you what's going on. Just put the page up on both screens. Recording and capture. Okay. So we're going to go back and look again, look afresh, get a slightly different view of the definition of the derivative. Okay? So there, we have the definition of the derivative. F prime evaluated at A, the derivative of F evaluated at A, is the limit of the relative change in value of F. Change in the value of F, F of X minus F of A, relative to change in value of the argument, X. And you're taking the limit of that as X approaches A. Okay, the first way is just a very trivial, in one sense, rewriting of that. So we'll express the other point x as the fixed point a plus a little bit, so a plus k. So we'll just rewrite the definition. So now we're taking the limit as k goes to 0 of f of a plus k minus f of a. A plus k is the new point, a is the fixed base point, and k is the relative is the difference between a plus k and a. and we're taking that limit as k goes to 0. That's just a simple rewriting of the definition, replacing x with a plus k. Okay, but now we start moving to our different view of it. So when we say that the fixed quantity f prime of a, the derivative of f of a, when we say it's the limit of that quantity on the right-hand side, well, the fraction on the right-hand side, really, we're taking the limit as k goes to 0 of it. So this quantity on the right-hand side, this fraction, is a function of k. Fraction has various values depending on the value of k. The definition, we're taking the limit as k goes to 0. But we're taking the limit as k goes to 0 of a function. So we can introduce an error function. So the error function we're going to introduce, we're going to use epsilon as the name for it. So epsilon is our name for the error function. It's a function of k. And what it's doing is it's measuring the discrepancy, it's measuring the difference between the value of the derivative of f at a and the value of this relative change in value of f. So remember, f prime of a is the limit as k goes to 0 of this fraction here. But if we kind of change our view of it, what we're doing now is we're viewing the existence of this error function, epsilon k, which measures the difference between these two. And that error epsilon is going to converge to 0 as k converges to 0. Because the definition says that the derivative of f prime a is defined as the limit of that relative change. Quotient as k goes to 0. Epsilon is the difference between the two, the derivative and the relative change quotient. As k goes to 0, epsilon k is going to be equal to. And then we take this definition of epsilon k and rearrange it slightly. We're going to make f of a plus k the subject of it, of that equation. So we've got to multiply both sides by k. And then move the other parts, f of a and f prime k times f prime of a over to the other side, and we end up with this expression here. f of a plus k equals f of a is f prime of a k plus k times epsilon. And this is a very important expression. We have this expression here. So, just going to write it out because I just want to add some annotation to this. So it's f prime of a, k times f prime, f of a plus k times f prime of a, k times epsilon. So there's various things going on here. This quantity here is the value of f near to a. Okay? The value of the function f close to a. This part here is what's known as the linear approximation. What we're saying is that the value of f close to a is given by this linear approximation, which we'll examine closely in a moment, plus this error term. And the error term has a particular property. The error term has the property that when you divide it by k, so certainly the error goes to 0 as k goes to 0. We kind of expect that. We're approximating something with an estimate and an error. As k, which is measuring the change, the distance to the new point, as that goes to 0, you get closer and closer to the base point. You'd expect the error to go to 0. But moreover, the error term divided by k, which is equal to epsilon of k, that goes to 0 as k goes to 0. This epsilon function, which we introduced a moment ago, we noted it had this important property that it converged to 0 as k converges to 0. This gives us is our alternative view of the definition of the derivative. Now, what we say is that the derivative of f prime of a, is the unique number. It's the unique number that slots in here, slots into this position, where you have the value at the base point plus k times something plus an error term, where the error term goes to 0 even after you divide it by k. So that gives us an alternative way to define this. So there's the unique number that goes in here such that we have this convergence property about the error. And that gives us an alternative way of looking at the definition of the derivative of that. The unique parameter that fits into this linear approximation, for which the associated error term converges to 0 even after you divide it by k. So the error term isn't just going to 0 because it's k times something. K is going to 0. The error term still goes to 0 even after you divide it out by k. And graphically, this relates very strongly to, well, it is the feature of the tangent line. Okay? So here's the blue curve here is our function f. The base point A is marked in the domain of f. And the red line certainly looks like it's the tangent line to the graph at that point. Looks like that the red line has the same gradient as the blue curve does at the point A. Now, when you view this picture in terms of the variable k, which is the difference between x and a, so it's the offset from a, so k, the origin of the k variable is, if you like, at the point A. K is 0, you're at the point A. K increases positively, you move this direction along the domain of f. K decreases, goes negative, you move to the left away from A. This expression here, f of a plus k times f prime of a, which is exactly the linear approximation, that's the equation of the tangent. Quite simple, it's the equation of the tangent. You recognize it as an equation of a line because it has the correct form. Students typically have in their heads that the equation of a line is y equals mx plus c. Y is the vertical coordinate, some constant m, the gradient times the x, the horizontal coordinate, plus the intercept c. Well, that's exactly that form here. So we have y, except we don't have x now, we have k as the horizontal, k is the horizontal coordinate. So y is some constant f of a, is the intercept, value of the height of the line at the origin, plus k times f prime of a, where f prime of a is the f prime of a is the gradient of it. So again, we're viewing the definition of the derivative now. Is the definition of the derivative is the unique slope, the unique gradient that gives you a line that approximates the function, blue function, such that the error term converges to 0 quite strongly. It even converges to 0 after you divide it by k. After you divide the error term by k of this quantity epsilon of k, which we know is still converging to 0 as k goes to 0. If we put any other value there in the place of f prime of a, if we change the gradient of the line, even if we changed it slightly, just imagine changing the gradient of the red line slightly, you would still have a pretty good approximation to the value of the function. Still have a pretty good line that's close to a. For points close to a, there's fairly good agreement between the red line and the blue curve. You can't really separate them. When you're close to a, they're kind of superimposed for a section around a. If you zoom in, they probably won't be, but at this level. So even if you change the gradient slightly, it'll still be a good approximation, but it won't have this convergence property here. The error term, you will still have an error term which is converging to 0 as k goes to 0. But the error term won't have this extra good convergence. If you change the gradient there, the error term that would be associated to that new linear approximation, it wouldn't converge to 0 as k, after you divided it by k. So that's a very important view of approximating the value of a function. It's something you'll definitely see this arising again, especially in second year when you start to look at numerical techniques of integration and solving differential equations, where we make use an awful lot of the time of linear approximations. Linear approximations are great because they're simple to handle. They're just straight lines or flat planes in the higher dimensional terms. So linear approximations are easy to understand in and of themselves because they're just lines, as opposed to some complicated curve suggested by the blue line. They're very easy for the computer to handle and to do computations with. And the computer can do very quick computations using linear approximations because it just has to figure out one little multiplication and then an addition maybe to evaluate the value of the linear approximation. So the study of linear and other types of approximations and the study of the behavior of the error terms are the two kind of major ingredients in numerical analysis, where you're studying the use of algorithms to approximately solve problems in integration, looking for solutions of functions, solving differential equations, and so on. So you're definitely going to see these themes reappear quite strongly in your study in second year and onwards. Okay? So it's good to be exposed to it now, to see it. And we're also going to make use of it. We're also going to see a key application of it here now, improving the chain rule. Now the proofs, they're maybe not they're maybe not as straightforward as the proof of the product rule and the linearity case. Okay? So the proof I'm about to show you, it works with manipulating this linear approximation expression for the two functions involved in the composition. Okay? So we'll look at this argument now, and then we'll go back to dealing with the quotient rule, seeing how the quotient rule can be resolved using a combination of the chain rule and the other problem. So we're going to prove the chain rule now. Did I put it in at the top of? Yes, the chain rule is here. Let's move to the two computers. So we're going to think about it very much in this form using the alternative notation, the dash notation. So this is what we're out to prove here, this equation here. So when y is defined as the composition of f and g, so y is the function f after g. We want to prove the chain rule, which is this expression here for the derivative of y evaluated at a, y prime at a. There is a good, strong, direct relationship between it and the derivatives of f and g, and it goes like this. We have the derivative of f evaluated at the point g of a, and that's multiplied by the derivative of g at a itself. Now, the assumptions that go into this is we have to at least assume, I mean, probably the safest thing is to assume that the functions f and g are differentiable everywhere. But at least what we have to know is that g is differentiable at a, and f is differentiable at g of a. Kind of minimum assumptions we need to make about f and g. But for ease of reading this, to begin with, we'll just assume that the functions f and g are differentiable everywhere. Okay. So how does the proof work? Well, we're going to use the linear approximation expression. Maybe I'll stick it back up there just so we can compare. Linear approximation expression. Now we're going to use it for the functions f and g. So we write down two versions of it. It's pretty straightforward to write down for the function g. So I just take the linear approximation expression for g, which is more or less that equation there, just I'm replacing the x with g. Pretty much translating that across. So that's the linear approximation for G, evaluated at points close to A. And it involves the derivative of G at A. Okay? Derivative of G at A is the unique number that slots in there to that equation that will produce an error term, this overall error term, which still converges to 0 after divided by K. We also want a second version of the linear approximation, this time for the function f. You have to think very carefully about where you want to base it. Okay? We see we're composing f with g. So the linear approximation for f that we want to quote and we want to make use of here is the linear approximation for f based at g of a. Okay? So we're copying the definition for f, but now the base point a, in this version here, because f is the second function in the composition, the base point a is now becomes g of a. That's where f gets evaluated at in the composition, that y is equal to f after g. So we have a version of that linear approximation equation for f. So for points close to g of a, so for g of a plus, say, offset L, I choose a different offset than the one k. K is in use for g. So the value of f evaluated at a base point g of a plus a little offset L is given by this expression here. The linear approximation to it is made up of the value of f at the base point itself, plus L times the derivative of f evaluated at the base point, and then plus the error term, which here will take the form of L times some function mu of L, on a different name than epsilon. Epsilon is already declared to be involved with g. F will probably have a different kind of linear function part, mu. And the key properties are, these are the linear approximations given by the derivative. So the error terms, which are k epsilon k, L, mu L, after you divide them by k and L respectively, they still converge to 0. So to this point here, to the end of that sentence there, is just kind of getting down clearly the two versions of the linear approximation equation for the functions g and f. So our task now is to, well, let's write it down clearly. Our task at this stage commentary on proof of 4.8. So what are we trying to do now? Now we're trying to establish, trying to discover what the derivative of y is. And this is the chain rule. The chain rule declares what the derivative of y is. So we're going to try and build the linear approximation expression for y. And what we hope to find is that it takes this form. I won't use epsilon. This is going to be a new thing again. So let's just, for the purposes of here, I'll represent that part of the error term with the new letter lambda, Greek letter lambda. The property that the error term I want the error term to have is after you divide it by k, so if you remove that initial factor k, it still converges to 0 as k goes to 0. And I've left a gap here because this is the place that's going to be occupied by the derivative of y at a. So what's going to go in here is the derivative of y at a. But I want to discover what that is. I can write it down and represent it there, but I want to discover what it is in terms of f and g. Because I know that this base point y is f after g, so I know what that's going to be. I know that y evaluated at the base point will be f of g of a. But I'm interested, we need to discover what goes here. And in particular, we need to establish the existence of and the convergence property of that error function factor lambda k. So this is our task now. So our task now is to find this, discover what fills this gap is, and prove the convergence, the necessary convergence of this, which is the lambda part. There's the two tasks we have to do at this stage. So that's our guidance, that's our scaffolding. That's kind of looking ahead, fully declaring what it is we have to prove at this point. It's always what you want to be doing as much as you can when you're in the middle of mathematical arguments. It's very difficult to build mathematical arguments where you're just kind of walking in the dark. You always want to set yourself goals and make it clear what the destination is at each stage. That guides you in the algebraic manipulation and the little logical moves you have to do to each stage. Always need to be clear on where you go. So we got to discover what goes in this cloud, and we have to find this function lambda and prove it has the necessary convergence functions. So that's what we start to do. So we begin with the y of a plus k on the left, and just start working with it as much as we can, using our two assumptions. And the two assumptions we have are that g is differentiable and f is differentiable. We've given ourselves the linear approximation equations for g of f. So we're going to work on y of a plus k, and wherever we can, we're going to substitute those linear approximation equations. Back them in wherever we can, because that will make use of them, and we manipulate them in some kind of way to move the expression towards this goal over here. This is what we do. So first of all, we can just use the definition of y. Y is the composition of f and g. So it's f of g applied to a plus k. Okay, that's just the definition of what y is, the definition of function composition. Because we've laid everything out so nicely, that immediately screams at us what to do next. Okay? So you've got that g of a plus k sitting there inside f. But just a few lines upstairs, we've written out one of our assumptions, which is an expression for g of a plus k. And it introduces factors k, and it introduces error functions. That's the kind of thing we want. We want factors k and error functions. So we go ahead and substitute. So we just simply replace this g of a plus k, we just replace it with this big right-hand side. So we have evaluating f at that big right-hand side. Now it maybe looks a bit intimidating at this stage because we've massively complicated it, kind of. We did have a very simple y of a plus k, and we got this big long expression. When you look at it patiently, compare it to assumptions that you've made, and you see again, it's ready and set up for another substitution, for another use of an assumption. If you look at this expression now, it's the function f evaluated at this big argument. But what form does that big argument take? It takes the form of g of a plus a bit. Yeah, the argument of the function f is g of a plus a bit. But we've made an assumption about such things. A few lines upstairs, we've made an assumption here about how to deal with values of f evaluated at g of a plus a bit. So that quantity L in the expression, what we're going to do is we're going to use L for this blue highlighted expression there. The value of L we're using, that's what I've highlighted in the blue highlight color there. So L becomes all of this, okay? And we make use of the linear approximation to F. So we just simply write out this right-hand side. We write out the right-hand side with the knowledge that L is the quantity k times g prime of a plus k times epsilon. So it's getting a little bit complicated. So what do we do there? Well, we just we draw out the bits we need. Look at the goal of where we're trying to get to. We're quite a bit of the way there. Look, we've got y of a plus k. We've got the first bit, f of g of a. We've got that. Okay? Compare the two expressions here. Compare the two bottom lines. We've got f of g plus a, What we want now is another term which is k times something. And then we want a big error term of some description. Well, in this second last line, we don't see k times something. All we see is an L. But look, within the L, there are k's. So within the L, there is this first bit, k times g prime of a. So we draw that out, okay? K times g prime of a is multiplying the derivative of f evaluated at g of a. So we simply write that part. The other part of this L here, which multiplies the derivative of f, the other part of the L is the k times epsilon k. That's an error type term. It involves the error function epsilon. So I don't write that down here. Instead, I bundle that up into this big function lambda. Now, unfortunately, the value of lambda written here, value of lambda written in the notes is conflicting with my use of lambda over there. Okay? I didn't realize I'd use lambda here in the notes. So the two lambdas are not the same. Okay? But we'll stick with the one in the notes. So what is this function, this error function lambda k here in the notes? Lambda k is all the other stuff. So it's going to include the L mu L, and it's going to include the k epsilon k times the derivative of f. So that's spelled out here on this line. Lambda k, so I've fully expanded it out in terms of k. This is the L in the square brackets, multiplied by mu of L, so I've expanded out L. And the first part then is the k epsilon k f prime g of a, the part that we didn't make use of in the linear approximation. So what we've got here in this blue part, this is our candidate for the linear approximation. Okay. It has the required form. It's f of g of a plus k times something. And the something, we recognize now, it looks like the correct expression from the chain rule. It's the derivative of f evaluated at g of a times the derivative of g evaluated at a. What I've got there multiplying k is exactly the correct expression from the statement of the theorem, from the declaration of the chain rule. So it's looking good. So we've kind of achieved our first task of finding this. We found this to be the correct expression, f prime g of a times the derivative of g of a. So that's good. This is as it's supposed to be. The final thing we have to do is prove the convergence of the error bit. So the error bit now we have is this total function lambda k, which is fully written out here. So all we have to do now is verify that when you divide it by k, you still have something that converges to 0. That expression there certainly does converge. The expression for lambda k does converge to 0 as k goes to 0, because this k is all over the place. Everywhere you look, there's a factor of k. That's going to make everything converge to 0. But what we crucially have to prove a little bit more is what happens when we divide it by k. Because from the definition of the derivative, it still has to converge to 0. So you simply divide it by k. We can do that because we knock off that factor of k there at the front. And here there's factors of k, there's factor of k in this square bracket factor, so we knock that out. So that's doing the division by k. So that gives us this new expression here. And then we just simply check and verify that it converges to 0 as k converges to 0. And it does. Because first of all, if you look at the various parts, but this first part, well, f prime g of a is just some fixed number, but it's multiplied by epsilon k. And epsilon k, we already know converges to 0 as k converges to 0. Secondly, we've got an epsilon k that converges to 0 here. Okay, this is a little bit worrying. We've got a fixed number here, fixed constant. That won't converge to 0. But of course, the fixed constant is multiplied by this function mu. Remember, mu was the error function we introduced associated to differentiability of f. So mu, we know, converges to 0 as its argument converges to 0. Mu of L converges to 0 as its argument L converges to 0. So we examine the way mu is used here. Is the argument of mu convergent to 0 as k goes to 0? Yeah, it is. K times a fixed number plus k times a function is convergent. So the argument of mu, this bit I'm highlighting here, that converges to 0 as k goes to 0. So although this is a fixed number here, g prime of a, it's multiplying a quantity that's converging to 0 as k goes to 0. So ultimately, all the different parts as necessary of the of the divided error function lambda k over k, all those parts are converging to 0 as k goes to 0. So that achieves the second. Have proved the necessary convergence properties for the error function divided by k associated to our linear approximation expression for y of a plus k. So we have established the chain. So I just have a little note there. That's probably the hardest, most technical part of it. Do take the time to confirm yourselves that this does have the necessary convergence property. It's a good application of all the different aspects of limiting process we've looked at. Linearity of it. Okay. So there's a couple of examples here to illustrate the use of the chain rule. In differentiating functions. So for instance, we might be given a function y, which is this expression here, x squared minus 1 to the power of 5. Now, one option you might take is to expand that out into a big, long polynomial. Expand out to the power of 5. You get a big, long expression, and then you could differentiate that without using the chain. But we can use the chain rule as well, because this expression for y is clearly the composition of two functions. One function is x squared minus 1. That's applied first to x. The second function is the raising to the power of 5. And we know how to differentiate. We know how to differentiate both of those. Probably easiest to jump to this second expression here. This kind of most matches the way we've been writing the chain rule here. Jump to this expression here. You see, first of all, we differentiate the second function in the composition. The second function in the composition is raising to the power of 5. We already know that the derivative of that function, raising to the power of 5, is 5 times the argument raised to the power of 4. So we put that there first. That's like the f prime evaluated at g of a. We then separately multiply by the derivative of g evaluated as we were dividing it. So the g function is x squared minus 1, so its derivative is 2 times x. We're also using the linearity property there. Derivative of x squared is 2x. Derivative of the constant term minus 1 is 0. So that application of the chain rule there, which you might tidy up a little bit, you got a factor of 2x and a factor of 5, so that's a factor of 10x. Still, you get it nicely represented in that compact form. 10x times x squared minus 1 raised to the power. As another illustration of it, we'd like to go back and prove our final part. So return to the quotient rule. The quotient rule for the derivative of a function f over g. Remember yesterday I explained how we could view that as the product of f with 1 over g. But we can view that as the product of f with the composition of r after g, where the function r is the reciprocal function. So this, if you look at yesterday's notes, if you weren't here yesterday, we finished off yesterday by setting up how we were going to prove the quotient rule with the use of the chain rule. We don't have to go down to any limiting expression arguments or any linear approximation arguments. We're just going to use the higher level properties. So the first thing I see here is I've got the derivative of a product. So I apply the product rule. Applying the product rule, this tells me I've got f of a multiplied by the derivative of r after g evaluated at a plus the derivative of f at a times the composition R after G evaluated at a. So that's by the product rule. We're not using limiting arguments for the definition of derivative, just using the higher level property. That's what the product rule says. When differentiating a product, it's the undifferentiated function times the derivative of one of the factors plus the other way around. The undifferentiated function R after G evaluated a times the derivative of the other one. What do I still have to work with here? Now I can apply the chain rule to this, because this is a composition. So this should be the derivative of the reciprocal function evaluated at G of A times the derivative of G evaluated at A. And here I've got, well, here I just have the composition function, R after G of A. So I'm going to apply the definition of R now. R is the reciprocal function, 1 over. So that's by the chain rule and the definition of R. Now another bit I need to simplify is I need to put in the definition of the derivative of R. We worked out the derivative of R from first principles yesterday. And we found that it was -1 over the square of the argument. Agreed? That was from the work yesterday that the derivative of R was -1 over the square of the argument. But I've applied that result there. Maybe it's starting to look like the quotient rule. So what have we got here? We've got adding together two things. They're kind of fractions. They've got denominators. The denominators are similar, G of A and G of A squared. So we can quite easily arrange that they both have the denominator square of G of A. Well, this term already has the denominator square of G of A, so we just write down the remaining factors in the numerator. I mean, minus f of A prime of A. This term only has a denominator G of A, so to make it over that common denominator, I need to multiply the numerator by G of A. Well, so that's f prime A G of A. And that's exactly the correct quotient rule. But maybe I have to change the order of those two terms. So that's exactly the quotient rule that's required. You're probably more familiar with seeing it maybe in the du dx or dt dx kind of notation, but just using the names f and g for the two parts of the quotient, that's exactly the we see here how it's a good application of using previous results. All the previous properties we proved from first principles using the definition of the derivative, either in its original form or our new linear approximation form that we saw today. But for the last property, the quotient rule, we'd already done enough work with the basic definitions. We already had enough tools in our higher level results, product rule, chain rule, and reciprocal properties of the reciprocal function to prove the quotient rule with a combination of them. Very good illustration of how kind of all your stuff fits together, gives you yet more results. Okay, so for the tutorials this week, you can work on finishing off this first version of the differentiation tutorial sheet. I'll have an extra sheet for you tomorrow on next week on the further topics in this chapter. So any of the remaining questions there that you haven't completed from this, you should continue working on. Some good questions there on extending the product and chain rules, generalizing to products of more factors and compositions of more components. Okay. So thank you for your attention, and I shall see you next week. I'll have